Hello, this is the second lecture for CHE211 that is focused on the different calculation techniques that will be used in the succeeding lecture of our analytical chemistry course. Here are the different expected learning outcomes for this lecture. First is we will recall the relevant units, prefixes, and conversions of measurements. Next is the calculation and conversion of different units of solution concentrations. Then, we will recall the calculations related to dilution of solutions. Fourth is familiarizing the different kinds of chemical reactions that will be encountered in CHE211. And then finally, do simple chemical stoichiometric calculations. So let's start with the important units of measurement. To express measured quantities, we will use the International System of Units, or the SI units, which is a standardized system that is based on the 7 fundamental units as shown in the table. These are called fundamental because these are the most basic units and may not be described as a function of other units. All other units of measurements, on the other hand, are called derived quantities because they are obtained from these base units. For example, density is a quantity that is derived from the base units of mass and length. To express very large or very small quantities in simple digits, prefixes are commonly used with units of measurements. You must familiarize yourself with these prefixes to properly know the multiplying factor that it gives. In addition, you must also be familiar with the common conversion factors, such as those for volume, mass, and temperature, that would aid you in the calculations for this course. Now, we proceed to chemical solutions and the different ways to express concentrations. This will serve as a review since most of these have also been discussed during your ENG201 course. So let us recall some of the terms. First, what is a solution? It is a homogeneous mixture of two substances, namely the solute, or the substance being dissolved, and the solvent. When we say homogeneous, it means that it has uniform composition and properties throughout the solution. Next, concentration. It describes the amount of solute in a given amount of solvent or solution. The amounts, as you will see in the next slides, may be expressed in terms of moles, mass, or volume. Electrolytes are substances which break up into cations and anions when dissolved in water, or in simpler terms, they ionize. There are two types of electrolytes which mainly differs on how they dissociate, whether partial or full, when placed in a solution. Strong electrolytes have full ionization in solution. These include strong acids, strong bases, and the salts. On the other hand, weak electrolytes only partially dissociate when in solution. Examples are the weak acids and weak bases. There are several ways to express units of concentration, but for this lecture, we will focus on these four, namely the molar concentration or molarity, percent composition, parts per million and the parts per billion, and the P functions or P values. So first, let's discuss the commonly used concentration unit for solutions, which is molarity. Molarity is defined as the number of moles of solute divided by the volume of solution in liters, or N over V. Its unit is expressed as capital M, which is equivalent to 1 mole per liter or 1 millimole per milliliter. There are two ways to express molar concentration. First is the analytical concentration with symbol C for species X, which gives the total number of moles of a solute in a given volume of solution. This, however, does not consider whether the solute ionizes in solution or not. Second is the equilibrium concentration, which is represented by square brackets. This describes the concentration of a particular species, whether ions or molecules, in a solution at equilibrium. To further explain the difference between the two, let us consider a 0.1 molar potassium chloride solution. Potassium chloride, when in solution, fully dissociates into K+ and Cl- ions since it is a salt. Its analytical concentration is just equal to 0.1 molar which describes that there's 0.1 moles of KCl in a liter of solution. It does not give the concentration of each ion species present in the solution. On the other hand, when you look at its equilibrium concentration, it shows that KCl as a compound is not present in the solution because it already ionized to 0.1 moles K plus and 0.1 mole of Cl minus in a liter of solution. Shown here are other mole-based concentrations that you may have already encountered in your general chemistry course. We have the mole fraction, which is equal to moles of solute over total moles. Next is molarity, defined as the moles of solute divided by kilograms of solvent, and normality, that is equal to mole equivalents of solute over volume of solution. Let us consider this sample problem. A solution is prepared by dissolving 1.26 grams of silver nitrate into a 250 ml volumetric flask diluting to volume. What is the molarity of the silver nitrate solution? To answer this, remember that molarity is defined as the moles of solute, or for this problem, silver nitrate, divided by the volume of solution, which is 250 ml. To get the moles of silver nitrate, we must divide the given mass of 1.26 grams by the molecular weight of silver nitrate, which is 169.9 grams per mole. And then we divide the moles by the volume of solution, but do not forget to convert the unit to liters to get molarity. And then calculating, we get the concentration of silver nitrate equal to 0.03 molar. Another way to express solution concentration is by percent composition. First, we have weight percent defined as the mass of solute divided by the mass of solution times 100%. This is usually seen in commercial solutions to express purity. For liquid solutes diluted in liquid solvents, it is more convenient to express in percent volume, or the volume of solute over the volume of solution times 100%. When using percent composition, whether by weight or by volume, it is important to note that units used for solute and solution must be the same for them to cancel. Sometimes the concentration is also expressed as a weight per volume percent when solid solute is dissolved in a liquid solvent. This is obtained by dividing the mass of solute in grams by the solution volume in ml multiplied by 100%. Now let us consider this sample problem. How much 7.5% by volume solution of ethanol in water can be prepared with 17.6 ml of absolute or pure ethanol? To solve this problem, take note that the given 7.5 volume percent here is equal to the volume of solute, which is 17.6 ml pure ethanol, divided by the unknown solution volume. So solving for the solution volume, we get 234.7 ml. For very dilute solutions, or solutions with very small amounts of solute, it is more convenient to use parts per million or parts per billion to express concentration. This is done so that simple digits may be used instead of scientific notations. Parts per million may be obtained by dividing the mass of solute by the mass of solution and multiplying by 10 raised to 6. Alternatively, it is also equivalent to mass of solute in milligrams divided by the volume of solution in liters. On the other hand, parts per billion is obtained using the equation mass of solute over mass of solution times 10 raised to 9. Or, we can also use mass of solute in micrograms divided by the volume of solution in liters. The p-value is defined as the negative logarithm to the base 10 of the molar concentration of a chemical species. You may be familiar with pH, an example of p functions, which describes the acidity or alkalinity of a substance. As an example, let us calculate the pH of 0.025 molar HCl solution. If we want to get the pH value, then we must only consider the molar concentration of H plus ions. Since there is 1 mole of H plus for every mole of HCl, the molar concentration of H plus is also 0.025. Getting the negative logarithm of 0.025 molar, we obtain a pH value of 1.6. Other relevant quantities that we have to consider are density and specific gravity. The density is defined as the mass per unit volume of a substance at a given temperature. Its unit is commonly expressed as gram per ml or kilograms per cubic meter. Meanwhile, specific gravity gives the ratio of the density of a substance and the density of water at 4 degrees Celsius. If the specific gravity of a substance is given, we can calculate its density by multiplying it by the density of water, which is 1 gram per ml or 1,000 kilograms per cubic meter, depending on the unit that you want to use. For the sample problem, calculate the molar concentration of nitric acid in a solution that has a specific gravity of 1.42 and 70.5% by weight nitric acid. To solve this problem, we must first calculate the density of nitric acid by multiplying the specific gravity by the density of water, which is 1 gram per ml. This gives us 1.42 grams per ml. And since the given concentration is in percent composition, a basis of 100 gram of solution may be used. To solve for the moles of nitric acid in the solution, first we multiply the 100 gram mass of solution by 0.705 to get the mass of nitric acid, and then divide it by the molecular weight to get the moles, which is 1.119 moles. Next, we calculate the molarity of the solution by dividing the moles of nitric acid by the volume of the solution. Take note that the basis that we have set here is 100 grams of solution. Therefore, we still have to calculate the equivalent volume by dividing it by its density and then converting it to liters. Calculating, we get a concentration of 15.89 molar. Finally, we move on to dilution of solutions. Dilution is done by adding more solvent in a solution, which results to the decrease in concentration of the solute. Take note that since the only component added is the solvent, the number of moles of the solute remains unchanged. Recalling the definition for molarity, the number of moles is obtained by multiplying the concentration by the volume of the solution. This gives rise to the general equation for dilution, that is C1V1 is equal to C2V2, where the subscript 1 represents the initial solution, while subscript 2 denotes the diluted solution. It is important to remember that the units used for concentration and volume must be the same for both sides of the equation. To further understand the concept of dilution, let us consider this problem. What volume of 12 molar HCl is needed to prepare 250 ml of 5 molar HCl solution? Since we know that the initial concentration is 12 molar, the final volume is 250 ml, and the final concentration is 5 molar, we can then substitute the known values in the equation and solve for the initial volume. Calculating, we get V1 is equal to 104.2 ml. Here are some self-assessment problems that you may solve to further practice the topics that we have discussed in this section. We will answer some of them in our synchronous section. So this ends Lecture 2. Thank you for listening.